Okay, now we are going to just carry on with where did we stop? In 2 minutes, we stopped here. What do we do when we have a pure torsion? Okay, so when you have a pure torsion, this is about chapter 6. This is where we stopped last time. Then what should you do? What should you do? You can go ahead and find, sorry. So you can go ahead, find SE prime using SUT. You can do that. You don't need to convert SUT into the shear ultimate, okay? You can do that. Then, if you need to correct it, Ka is been developed as a function of SUT. أي material يا شباب, regardless if it is subjected to cyclic bending or shear or axial, doesn't matter. Ka is related to the surface and it was correlated with SUT. So you can use A SUT to the power B. You don't convert it into SUS, which is the shear yield. No, this has nothing to do with it. Now, so this is done, this is done. For KB, the equation, يا شباب, for KB, اللي هو size factor, clearly tells you, if you go back to the book, you will clearly, يا شباب, understand that if you have bending loading or torsion loading, either one, you should use KB from the diameter. That's it. You know the diameter and then you know the equation. Later, we told you that if you have either torsion or bending together, you know, or with axial, whenever they exist, you can go ahead also and find KB using the equations. No big deal about that. Now, however, KC must be applied as 0.95. Now, this is gonna fix everything related to torsion. You understand? Now, what is the Q shear? Because you have torsional loading, and if you have KF, what is gonna be? Q shear, ya shabab, if you go to the book, it's for shear. However, the curves were given as a function of SUT. So they know, instead of giving them to you as function of ultimate shear, they gave them to you as function of ultimate intention. So don't worry about it. Use the ultimate intention for the material in that figure, and you will find the Q shear for the shear loading. So you don't need to worry about it. What you need to worry about are A and B. A and B for the equation sigma reverse equals to A n to the power B. هذول يا شباب, they have A equals to what? F SUT square divided by SE. Now, SE is corrected for shear because you multiplied it by 0.59. But what about the ultimate strength here? You should convert it to shear. And this is what you should use. SU or SSU, the shear ultimate is 0.67 multiplied by the ultimate intention. The same is done for B. B equal minus 1 over 3. The log of F SUT divided by SE. So again, SUT has to be corrected and must be converted into SSU. Do you understand? If you use equation like Gerber or Goodman, which needs yielding, don't forget that we should convert the yielding into a shear yield using von Mises, which is 0.577. Okay. I hope this clear it out for you. Now we are going to start chapter number 7. Chapter number 7, ya shabab, is completely dedicated for shafts. Of course, this is very important because shafts are a very significant element, especially in rotating equipment. طبعا إلى اليوم يا أخوان ما في غنى عن الشافت. Why? The wind turbine, which is supposed to be you know, one of the like new generation method to generate electrical energy will need a shaft. It is not like solar panels. Solar panel take the sun and convert it right away to electricity. But waves, whether they are coming from waterfalls or wind, they need to convert that mechanical rotation into electricity through the transmission of the power on the shaft. So shafts are very important. We're going to talk about a little introduction. Then we'll talk about shaft materials, layout, design for stress, and then some deflection, as well as miscellaneous shaft components. So what I want you to understand from this is that shaft, this is the definition, shaft are rotating members. They are usually circular, and most of the time, they are used to transmit power or motion, okay? And what you should understand is that shaft, ya shabab, are, you know, not necessarily uniform. They're shaft. It doesn't mean that they have the same diameter, which we are going to see next. Now, what you should understand is that there are two important factors for shaft. The first one is the safety of the shaft with respect to yielding, fatigue, for example. And this is usually guaranteed by calculating the factor of safety, NY and NF. However, there is another problem, which I talked to you about, like, you know, many lectures in the back, which is in the past, I mean, which is the deflection. Now, as we said, shaft or mechanical element inside those rotating machine are aligned and clearances are very, very tight. And whenever those clearances are closed, then things will start rubbing into each other. And once things start rubbing into each other, we will have a big problem. So your basically machine is gone. So deflection might ruin this clearance or those clearances. And we need to be very careful about it. But if you remember, ya shabab, from chapter 4, whenever we talked about Castigliano theory or any other method, like the section method, we always see EI in the deflection. And it is not surprising. Why? Because deflection, look at this statement, ya shabab. The deflection and the slope analyses cannot be made until the geometry of the entire shaft has been made, okay? And why is that? Because in reality, the deflection depends on the entire geometry. فمثلا احنا في stress analysis, if we have the shaft like this, for example, we know that this region will be affected by the fillet, and the stress in this region might go high just because of the fillet, but this region may not experience anything. Away, it doesn't matter. Locally, we have a problem. However, deflection is different. Deflection tells you, I need to know the entire diameter of the whole thing, and then I will tell you how am I going to deflect. You change something far away in the right end, you get different deflection in the left end. It's a function of everything, not like stress. Stress is local. As far as you know the diameter here, you know the diameter here, you can calculate the stress concentration factor, and then you may find the stress at this point, which is very dangerous. The rest has nothing to do with anything with it. So that's why we have a very important statement that says that deflection is not affected by strength, but rather by stiffness, which is represented by the modulus of elasticity and the geometry, in another word. That's EY. That's EI, I mean. So in another word, ya shabab, if you made the design and the design was safe, the factor of safety, let's say, is 2.5. So what do you need to do? Let's say you discover that the deflection was high. It doesn't matter يا شباب انك تروح تقول انا بستخدم steel which has higher ultimate strength and the deflection will get better. You will get nothing. Why? Because if the modulus of elasticity is the same and you don't want to change it, the only thing now is the diameter. Putting more strength will not help you out with deflection. For this reason, it says, rigidity cannot be controlled by material decision, but only by geometry. Okay? Now, as a general rule, many shafts are made from low carbon, cold rolled, and hot rolled steels like AI 10120 and ANSI 1050. Now, if you go look at these steels, so you will see that their strength is not huge, okay? And you need to notice one thing is that fatigue failure is reduced moderately by increasing the strength. So in another word, if you increase the strength, you may not get too much benefit. And I'm going to give you one little example here, is that you don't need always to increase the strength. In reality, ya shabab, what we said about fatigue is that it is related to the idea of crack initiation and then the crack growth. Now, what you need to understand, which is, by the way, explained in one of the sections of chapter 6, I think, which is a fracture mechanics. Unfortunately, we don't cover this in the material of the book, but of the course, I mean. But what the fracture mechanics is telling us is that if you have a crack and the material is brittle and you applied a significant load, which is, you know, capable of propagating the crack, in reality, crack might grow in the material if it is too brittle in the speed of sound. That's too fast. The best example is the tea little cups يا شباب. على اختلاف الثقافات يعني في المنطقة هنا في السعودية كلها، في ناس تسميها استكانة، في ناس فنجان، whatever. Now, that little, actually الفنجان نستخدمه حق القهوة بس whatever. That little cup for tea, you have probably even see it. When you pour the tea, sometimes it's just cracked open into two halves. No warning, no sign. That's what we call a brittle fracture. Now, the harder the material, the more it behaves like a brittle. That's the meaning here. Actually, crack turns out to be like if you have a plasticity, it makes the crack goes like in a mud, so it slows it down. Of course, this is not as simple as this. There are too much detail in there, but this is the general idea that you don't need necessarily to push for higher strength in order to get better performance. So shaft as a layout, ya shabab, in general, they are designed to accommodate element. يعني الهدف من الشافت هذا مو هو. It's not the main purpose. The purpose of the shaft is to carry things. Those things are the things that does the job. For example, we can put gears, bearing, pulleys, and others. And in general, we usually have a stepped cylinder design for shaft. That's why shafts are usually like this. And you may ask questions why and why not, then we'll talk about it later. But usually it is a step. There are steps for the shaft. Oh, sorry, Shabab. So now what you should understand is that it is not necessary to analyze every single point in terms of stresses for the shaft. Because as I said, and I'm still saying it, you are actually having infinite number of points. So you don't know. You don't need to do everything. But what we usually do is we depend on our understanding. For example, the locations where moments are high, those are going to be dangerous, where torque is high, and the locations where we have stress risers, like key or holes and so on. You understand? So, so these are some examples of shaft. As you see, shaft are already usually well taken care of because they are very important element. So usually you will see shaft very shiny, clean, no scratches and no cracks and so on. And they can come into different sizes. Of course, you can see here that there are steps. They come into different sizes. This is just to give you a scale. This one could be like 50 centimeter in diameter. That's half a meter. This is a huge turbine. Remember يا شباب التوربينز اللي يستخدموهم في القرية أو في الجعيمة شركة الكهرباء عندها power generation station. They don't have thousands of turbines. They have maybe 5 or 6. And those turbines are so gigantic. You can even drive your car inside it. So the rotor, which is the turbine, the shaft, as well as these expensive blade that I talked to you about, you know, are so heavy. Sometimes, I mean, not sometimes, you need to bring a special crane just to lift that shaft. 100 ton, 70 ton, something like that. So this is to give you a scale. This is, I think, a very huge. This is like a 5 megawatt. Okay, that's 10 times the wind turbine that you are working on for your project. You can see the individual over here sitting between those blades. And of course, this is another one. This is an individual, a machinist sitting here. This is probably like maybe not less than 70 centimeter in diameter. And probably the reason why, you know it, right, is deflection. It's probably very safe in terms of fatigue. But as we told you, if you're going to make it from steel, which is the best material, you will end up only controlling the deflection by increasing the geometry, although it may not be necessary in terms of fatigue or yielding. This is an impeller, ya shabab, that usually used to be mounted on top of the shaft. This is a very nice looking shaft. It's a straight shaft, which is not very common. And as you see here, there are flanges where you use this to connect the shaft with other mechanical elements. Now, إذا تذكرون يا أخوان, if you remember, when we talked about bending and torsion and shear force and axial, I told you that we will end up one day saying that we don't need to deal with shear force V, Q, I, T. You go and you take this big gigantic diameter and you apply a shear force of 10,000 Newton, you get a stress maybe 5 megapascal. It is nothing. Same, if you apply F over A over this gigantic steel cross section, what will you get? You'll get a normal stress of maybe 5-10 megapascal. But just like in your turbine shaft, if you apply a torque like the one in the problem for the project, 395,000 Newton meter of torque, if you go and calculate the shear stress tau equals to TR over J, you will get a high. Remember يا شباب, if we use low carbon steel alloys with a yield strength maybe 400 megapascal. What did we tell you about the yield and shear? It is based on von Mises 0.577, which is approximately half. So the yield in torsion will become 200 megapascal. And if you apply tau, which is 395,000 Newton meter over a small diameter, your stress will shoot up. It will make it, even if you make it a little bit big, you might get how much? Like 180, 150 megapascal of shear. And you have only a yield of 200. You are very, very in the very dangerous zone. So you can easily get a high shear stress from torque. Same goes with bending. Bending of a few hundred, few thousand Newton meter can easily push the stress to several hundred megapascal. And we know that the yield stress is only several hundred megapascal. So this is where the problem comes. عشان كذا يا أخوان, for the sake of design, we are going to ignore the axial load because of tension and the shear load because of shear force. And by the way, if you want to be comfortable, you can calculate them in your problem. And you will see that they are so insignificant. عشان كذا, the problem now for shaft become really interesting. Why? Because, we know that shafts are round, which means we can use I and J for a round cross section, which is pi over 64 d to the power 4. And because shafts are subjected to huge loading, we will not use hollow. And for that reason, we're going to use a solid shaft. So what are we going to do? Shafts rotate with high speed, which makes them just like the rotating bending specimen. So fatigue is very essential. For that reason, we will jump right away to the equations. What are we going to do? We are going to express the amplitude from bending and the mean using the bending equation. And just in case, because we know that we have fillet, keyways, and so on, we are going to make it ready by applying KF. If KF is 1, nothing is going to change. If KF is not 1, you're just going to apply it in the equation. And now we will also deal with torque the same way. We will have TAC, which is C is the half of the diameter divided by J, and then we will multiply by the fatigue stress concentration factor. Now, we know that we are going to also use solid shaft, so why should we keep it I and J? So what are we going to do? For solid shaft, we will open up the equation and we will have pi over 64 d squared d to the power 4, and we will, divide that by 2 because we have C equals to d over 2. That's why we have 32 over pi d to the so on. Now, if we know these equations and we know that this is what we are going to use, those are multi-axial loading. One of them is bending, which is normal. The other one is torque, which is going to create shear. So how do we combine them together? We use our friend, which is von Mises. So von Mises will allow me to find the equivalent amplitude and the equivalent mean by applying the amplitude from bending and the amplitude from torque, as well as the mean from bending and the mean from the torque. But remember one thing, I don't need to keep sigma A unknown. In the past, we say sigma A. Why? Because sigma A can come from tension, can come from bending. Here, tension is not important. So what are we going to do? We're just going to ignore it. If the tension is not important, we know what is sigma A. It is 32 kf MA divided by pi multiplied by d to the power 3, which is this. So what are we doing here? We are supplying the equations inside von Mises. We don't need to keep them simple, like sigma A, tau A, because we know what is inside them. Now, if we know يا شباب what is inside them, then Goodman says sigma A prime divided by SE plus sigma M prime divided by SUT is equal to 1 over N. So the question, can I take all of this and plug it here, and then I take all of this and plug it here? Of course, yes. You'll have a big equation, but if you rearrange the equation, you will get a very neat end equation. And this is what we have. This equation, ya shabab, is called the distortion energy Goodman equation or design equation for solid shaft. So someone who was probably the author of the book was very kind to rearrange this equation twice. One time to solve for 1 over n. So if you solve for 1 over n, what does this mean? Everything in the right-hand side, you plug it inside, you get 1 over n. You flip it, and you find n. By finding n, you know if you are safe or you are not safe. The other equation is the design for the geometry. What happens if you want to know the diameter? Which everybody was asking me for the project. What is the diameter? How do we know what's the diameter? So if you know the طبعا هنا يا شباب, this is the confusion part. To find the endurance limit, you need to correct for KB. KB needs a diameter, so you don't know SE. صح? In order to find KF, KFS, you need the diameter. So it's like this equation is not solvable. In another word, this equation needs a numerical solution. The right-hand side depends on the left-hand side, and the left-hand side depends on the right-hand side. However, why this equation is so beautiful and helpful, ya shabab? Because of this. There are general guidelines. يعني مثلا الآن انتو شو يعني لكم, what does it mean to have a project which says that you need to design a wind turbine for the low speed shaft to transmit a power of 500,000 watts. What does it mean? تيجي تقول لو أنا سألتكم, what do you think the diameter of the shaft should be? 10 centimeter? 20? 40? 50? You don't know. Honestly, you don't know. What you need to know is a good guess. Good guess. If you don't know a good guess, شو تصير؟ يمكن أنت متحفظ, conservative. تقول no, I don't need to make it 30. Let me start with 10. You do all the calculation, KA, SE, and so on. You find the factor of safety. The factor of safety is less than 1. تقول طيب. خليني أخليه 20. And then the factor of safety becomes less than 1. And then 30. And then 40. And you spend weeks working on the problem. What you need is a good guess. Good guess إنه هو كذا. مثلا أقول لك, there is a good assumption to start with SE like 100, for example. And then KF, KT to 1.5, something like this.
الصوت راح يا دكتور. يا دكتور
ما في صوت يا دكتور.
يا دكتور ما في صوت يا دكتور.
Okay, يا شباب. I am very sorry. I got my iPad got disconnected. Can you hear me now again?
Yes, we can.
Yes, دكتور.
Okay. So what I was saying that basically this diameter equation will give you a good estimate. Okay. And the good estimate might be not too far from the right answer. So you start with it and then you start making good assumption and correct them. Of course, since we have it for Goodman, we can have it for Gerber, as you see over here. And we can have it for the elliptical equation. And we can have it for Söderberg. There is only one note, if you remember, that Söderberg is the line between SE and SY. And the Langer line is going to go like this, between SY in the y-axis and SY in the x-axis. For that reason, if you decided to use Söderberg, you don't need to check for yielding. But if you use other equations like Gerber is like this, you have to design for yielding, or you need to check yielding. And to check yielding for example, Goodman or Gerber, you need to check yielding. And for ASME elliptic, you have one part which is below the yielding and the other part which is above the yielding, and you need to be careful. But in general, you better use the maximum equation using Goodman, using the distortion energy, which is von Mises, to find the maximum equivalent stress, and then divide SY by that maximum to find the factor of safety, guarding against yielding. I'm gonna stop here, ya shabab. I'm gonna ask you to kindly turn on your webcams, because I am going to take the attendance, and then we'll continue this inshallah next class. Okay. You are allowed to leave right away after calling your name. Who do we have here? Hussein?
Yes.
Okay, Saleh?
Yes, yes.
Saeed?
Yes.
Adnan?
Yes.
Adnan is here? Yeah, okay. Muhammad? Madan?
Yes, here. Here.
Saleh Sultan is here.
Yes.
Ali?
Yes.
Ali? Walid?
Yes.
Faisal?
موجود دكتور.
Okay, Ali?
Yes, دكتور.
محمد؟
Yes, دكتور.
مفلح؟
Yes, دكتور.
فهد؟
موجود.
رين؟ فيصل؟ Faisal, are you here? Maslih is here.
Yes.
Salman?
موجود دكتور.
Faris?
Yes, موجود.
Khalid?
Yes, موجود دكتور.
Saad?
Yes, دكتور here.
Umar?
دكتور.
Samir?
Yes, دكتور.
Mustafa?
Yes, دكتور.
فواز العوفي أمجد
يس موجود.
فيصل
Yes, دكتور موجود.
محمد no Faisal yeah I remember that Muhammad is here okay
Yes.
Nasser عبد الرحمن
Yes, دكتور.
Umar I see you Muhammad you're
Yes.
here and Muayyad
Yes, present.
and Muhammad
Yes, دكتور.
okay that's it يا شباب thank you so much